Okay, good afternoon. Welcome to everybody. Welcome to the second seminar of this Spatial Data Science webinars. And I will pass straight away to the topic of this seminar, which is subsoil image reconstruction by using generative adversarial networks. And this seminar will be given by Helga Jordão. Helga, please, the stage is yours.
Thank you. So first, thanks for this invitation. And in this presentation, I will show you how we can use machine learning, particularly deep learning, to improve subsurface modeling. And what is subsurface modeling? Subsurface modeling is a numerical representation of the subsurface over a specific volume of interest, a volume that we want to distinguish from the other parts of the subsurface. And some examples are oil and gas reservoir, aquifer, or mineral deposits like copper or gold. And the subsurface models are based on physical measurements of the rock or fluid properties. The measurements can be direct as drill hole samples at a very small number of locations, or indirect using seismics. And here we have an image of a mineral deposit where we can see the surface, the drill holes, and different regions. And we mold these regions separately because they present different statistical distributions, including univariate, bivariate, or spatial. And geostatistical methods have been successfully applied to model the subsurface in many cases. However, there are still cases where geostatistical methods or other type of methods are not a solution. So in this work, we apply deep learning in such a case in a complex geological environment, a mineral deposit located in south of Portugal. But before I dive into the methodology applied, I will focus on the importance of geological modeling, especially in the present time where climate change is a global concern. So the world is rapidly progressed to low carbon technologies such as wind turbines, solar panels, and battery storage to combat climate change. But these technologies require large amounts of metals and minerals that must be mined. Just for example, one turbine of 3 megawatts needs 4.7 tons of copper alone. So, in other words, clean energy transition will be significantly mineral intensive, and we must ensure minerals are mined in a sustainable way. And there are many opportunities in mining to achieve this responsible extraction and processing of minerals and metals while minimizing carbon and material footprints. Energy efficiency in mineral value of change. At the present, mining consumes 11% of the world energy. Innovation waste solution to protect people and the environment, and robust geological data management. And here lies this work that by having faster and more robust geological models, investments and operational decisions will be based on more reliable resources predictions that will lead to lower waste generation and energy consumption. So as I said, in the evaluation of mineral resources, we divide complex mineral deposits into four types, which are mineralized bodies with homogeneous geological characteristics. And using geostatistical methods, we estimate the hoard grades like copper or zinc within these boundaries for each hoard type. And as I mentioned, when the geological environment is complex, geostatistical methods for characterizing the spatial distribution of the boundaries, it's not of the hoard grade, but the boundaries of the hoard type, geostatistical methods are not a solution in most of the situations. So typically the different hoard types are interpreted manually by an expert geologist. So at the present, there is no effective way to avoid intensive expert geological interpretation of hoard types, boundaries, in mining routines, which is highly time consuming and a severe limitation of the need for geological resources to be frequent updated. The example that I will present from a mine located in south of Portugal, it takes 1.5 months to update the entire model. Therefore, there is a temporal gap of 1.5 months between the arrival of new drill holes information and the new version of the geological model. And remember that all the decision-making, investments and operational decisions are based on mineral resources predictions. So to tackle this problem, we propose a deep learning model to mimic the process of manual interpretation by an expert geologist of a given geological environment, and how the system learns from the historical data from a given area of the mine with drill hole samples and the corresponding geological models constructed from these samples. And second, it can reproduce this modeling capacity in the same geological environment, but in new situations in which only new samples are available. So the proposed method is applied to a real case, a sulfide deposit located in south of Portugal. It is a complex mineralization of copper and zinc with several ore types. Just an area with just two ore types, stockwork and massive sulfide, and the barren rock was chosen. And how we prepare the data set. Since we only have access to one 3D geological model, we selected from this 3D geological model two-dimensional vertical parallel sections along the model. The drill hole samples falling on each section were also selected. So the database was composed of those of the geological model, the one drawn by the geologist, and the drill hole samples that fall in each one of the sections. So the total database was randomly divided into the train and test data set, the train to train the neural network and the test to evaluate the results. So the deep learning model implementing this work is called Generative Adversarial Network. It was first presented by Ian Godfellow in 2014, and it has been applied in many fields. Face generation is the most known. And what is the main difference between a GAN and other deep neural networks? In a GAN, we have a neural network that is called the generator that has a function to generate 2D or 3D outputs. The generator has an input. This could be noise or some data that we wish to condition the output. This information passes through the generator, which produces an output that we call here fake. On the contrary of other deep neural networks, the generator is not updated directly by the error committed by the generator output. Instead, we have a second deep neural network that has the function to classify how real is an image. This neural network is called Discriminator, and it receives real or fake image, classifies the image given a probability of being real between 0 and 1, and is with that classification that the generator is updated. And this is called the adversarial loss, which is the capacity of the discriminator to correctly classify real and fake image. Thus, for the generator, we want to minimize this adversarial loss because we want the generator output to be classified as real. But at the same time, we want the discriminator to correctly classify real and fake image. And because of this battle between the two neural networks, the distribution of the generator data will converge with that of the training the real data. And the discriminator will not distinguish between a fake or a real image. In this particular case, in this study, because we want the output of the generator to be conditioned to an input, the generator is also updated via L1 loss, the absolute difference between a real image and a fake image. So the discriminator is a deep convolutional neural network. The input is both a conditional image, which in this case is, will be the drill hole samples, and the reference image that can be from the trained data set, the geological models drawn by the geologist, or it can be the fake image, the one that was generated by our neural network. So the discriminator must predict whether or not this reference image is a positive transformation of the conditional image. The generator is a UNet, which is an encoder-decoder framework that uses skip connections in between. The skip connections allow local patterns from the conditional image to be transferred directly to the generated image, since certain finer details may be lost during the encoder stage. And the generator takes the conditional image, which are the drill hole samples, as an input, then passes through a series of blocks of layers, and the output is a 256 by 256 pixel image of the geological model conditioned to the drill hole samples. We also modified this UNet to perform a Bayesian inference through Monte Carlo sampling using dropout. Dropout is a regularization technique used to avoid overfitting that randomly ignore or drop out some number of layer outputs. Since in every iteration we randomly sample neurons to be dropped out in each layer according to a dropout rate, each time the model's architecture is slightly different, and we can retrieve multiple Monte Carlo samples by processing the input several times. The resulting outputs can then be averaged to recover a single estimate of the geological model, and the variance between samples can be taken to estimate the epistemic uncertainty. So to enable this, epistemic uncertainty estimation, we incorporate dropout after each convolutional block, except in the last block, and different dropout rates were studied. So in resume, this is our generative adversarial network. The input during training, the input of the generator are the drill hole samples. It passes through the generator, and we have this geological model, which we will call the fake, or the generated by our UNet. We pair the geological model with the drill hole sample, and we pass through the discriminator that gives a classification how real is this image. With that, we optimize the generator, but we also have the difference, the absolute difference between the fake image and a real image. The discriminator is updated only via adversarial loss, so we give pair that come from the data set, which we call the real pair. We pass it through the discriminator. At the same in intervals, we pass fake pair, and we optimize the discriminator just via the adversarial loss. So to evaluate the quality of the geological models generated, we use the following metrics: intersection over unit, which measures the overlap between two areas, and the mismatch at sample locations. And before showing the results, I would like to show a very small video of the training phase. Here we will see the generator being trained. So at first he will produce almost just noise, then he captures that he has a mineral deposit in some direction, and then we do not have just one class, but two classes of core type. This is almost noise, and it tries to perfect the boundaries between the core types. So passing to the results. First, we evaluate the different dropout rates for both the metrics, intersection over unit, which we want the higher value, and mismatch, which we want lower values. The benchmark was our generator without dropout. This is the results, and using dropout. And we can see that by using dropout, we have a better results than without using. This is due to overfitting. Dropout is a regularization term that improves or minimize overfitting. So so that's why we have better results. And here in the mismatch, we can see that for dropout rate of 20%, we get the lowest value. So we selected this value of dropout rate of 20, and then we evaluate the results. So for this dropout rate, for the for the average of all the samples of the test data set, we achieve 4% of mismatch at sample location, which is a really low value, and intersection over union for the Stockport, which is the gray area, 95%, and 87% for the massive sulfite, which is the yellow area. So here we have, when I say real, this is the models drawn by hand, we can say by the geologist, and this is the image produced by our neural network. And these examples come from the test data set. So the neural network during training never saw this image. And we can see that they are very nice image. Of course, there are some areas that we see that it's not perfect, like here or here. But in overall they are very good results. Passing to the evaluation of uncertainty. Here we can see we have the models again, 2 examples, and here we have the models drawn by the geologist and the models drawn by our neural network. This is the average of 100 estimations of the same input, and here we have the variance obtained from these 100 estimations. And we can see that there are variability by using dropout, so the output is slightly different each time we pass it through the neural network, and the higher values of variance are in the boundaries between the ore types and the barren rock, the exterior area, and the higher values are in this external boundary, but we can see that we have medium values when we are in the boundaries between the stockwork and the massive sulfite. We can see also that in some areas it's not very easy to see that here and here we have very low values of variance, but not 0. And we can see that they are in a zone that is homogeneous. So the neural network here has some doubts if possible, if we have here the massive sulfite, the yellow ore type, or not. So in conclusion, that the present geostatistical methods do not present a solution to model complex geological environments. And this task is done mainly by a geologist. Thus, to tackle this problem, we propose again as an end-to-end framework for generating geological models conditioned to drill hole samples. And the results and validation show that the geological models produced can be extremely accurate and perform well compared to the models obtained by the geological interpretation. We believe this study presents very promising results for geological core type modeling in real-time framework. It is important to note that this methodology presents a huge reduction when compared with the time consuming of a geologist to manually perform the test, from 1.5 months to less than 1 hour, including the quantification of uncertainty using dropout. It is none of the less important to continue validation experience in various settings prior to the use of the real-world decision making. Thank you.
Okay, thank you, Helga, for a very nice presentation, nice and clear presentation. Well, we have some time for questions. Just, okay, I will start the question, and I will start by some of your conclusions. One point of your conclusions, when you said that when you said it's this kind of models of complex bodies, in this case geological bodies, always require some expert integration, geological interpretation. Okay, always. And geostatistical models, which is quantitative models, need always some kind of expert conditioning. Like, for example, in when there's some discontinuity, the expert, the geologist must say, well, can be by a folding or fold or whatever. That's why I think the scope of your work is quite interesting, quite innovative. You do not try to reach the unknown reality, the unknown limits of the bodies, but you try to mine the expert interpretation. This is that's why you train your two networks with the interpretation of historical cases. Okay, that's now my question. Because you have no time to clarify that. This method implies that when you apply your GAN in a given environment, this environment, I mean geological environment, is supposed to be stationary. I mean, you cannot train again here, or you can. I don't know. You can train again here, and that is valid for all kind of geological environment.
No, I don't think so. I think you cannot generalize the neural network, because for each type of environment, you have different characteristics. So the geologist also learns along the time how is the environment, how is the distribution of the host types. So in geology, it's always very different, even if it's from the same environment, like a volcanic sediments like we are seeing here. Probably we need to always train the neural network for each specific environment.
Yes, I agree. Just
you don't, sorry, Helga, you don't think you could use those kind of transfer learning techniques to move from one? Maybe we will not to retrain everything since the beginning.
Yes, maybe if it's in the same environment, like in a mine that we have different deposits, that they are all of them are have the same source. We can use both data from different deposits in the same area and retrain, not start from the very beginning. But I think that we will always need, because we will have faults and specific geological characteristics that will be particularly for each case. And a fall, it's something that probably will be there in our work.
Thank you.
Can I ask something?
Yeah.
Hi, Helga. Nice talk. I'm very interested in your methodologies to apply in other areas, of course, as you can imagine. Did you try other type of deep learning techniques, or you started with this?
I started with this. I did research. I only apply with this type of architecture, the UNet and the generator as a unit, and the discriminator as a typical convolution neural network. But I studied different loss functions or different number of layers. But in general, I just did apply this.
You choose, okay.
Yeah.
Thank you.
Can I have a try also on a couple of questions? On the same line that Rita was asking, I was wondering that if you may change the structure of the neural network to adapt regarding the type of variables that you have, or that type of neural network is more static. How do you use mostly the distributor part?
I don't know if I understood, but if I can have different inputs of the no.
Yes, but also how do you stipulate how many layers, hidden layers or neurons? It's your choice, or
it's my choice. There is no
supervised or unsupervised, the choice.
This is a mix between unsupervised and supervised, because the discriminator is using the discriminator is an unsupervised method. But since I use the absolute difference between the real geological model and the fake geological model, this is also a supervised method.
Thank you.
The number of layers and the number of filters, because this is a convolutional neural network, is defined by me. Of course, if we have a neural network that is too small, it's probably do not give you so good results. But from a certain number, this is not defined. You have to test. You will have good results. You have to be careful of overfitting, because when your neural network is too good and your process, what you want to achieve, is very simple, probably you will have overfitting.
Okay. And regarding the dropout process, do you impose a limit for the dropout and compare for the several different thresholds, or how do you do it? I never worked with dropout.
Dropout shuts down the neurons randomly, but I can define how many I want to drop out for each layer. So I can say 20%, 1%, 50%. So I
like an accuracy level or not?
Sorry?
Like an accuracy level or not, as we do in statistics with the tests.
With the results.
Yes.
Do you compare when imposing a certain dropout? You compare the results attained for the different thresholds.
Yes.
Thank you.
Thank you for a nice presentation. It was very interesting. Thank you.
Thank you.
Okay. Any other question?
Just another. Which package are you using with for the convolution and the
Keras.
Okay. Thank you.
Yeah, it's very simple. The Keras, it's very simple to use.
Okay. Well, I will have a last one, and as I said, this is one of the biggest and important challenges of the mining geology routine, in a mining routine, which is to achieve, to try to get the boundaries of the unknown geological bodies. But another, and I think you got a solution, a possible solution, and a good one. But another issue, which is extremely important when you try to see what's going on inside each body in terms of metals, and it is the uncertainty. And you mentioned that the method that you try now with this dropout, you reach some level of uncertainty. Okay. So, but you find out some limitations, right? Or I didn't understand or no?
Yes, I consider that this technique of dropout has some limitations. Mm-hmm. So by a mining engineer or geologist, we know where we want to have uncertainty. So uncertainty should be dependent how much complex is the local. And when analyzing these results of uncertainty, we do not see that very well, because the massive sulfide, that was the yellow one, that was within the stockwork, have lower values of variance than the limit that that is the boundary with the external boundary. And the external boundary is more homogeneous, more continuous, and we have the higher values there. So we still have to do more tests and evaluate or try different techniques to achieve what we are expecting, the areas that we expect to have higher values.
Okay, thank you, Helga. Well, as I don't see any more question or raising hand, it's time to finish and to close this section. Time to thank Helga for this very nice presentation. Thank you, Helga. And I would like to thank you the presence of all of you that made this seminar, well, a good event. Thank you. And keep safe.
See you.
Okay, because
you too. Bye-bye.
Bye-bye. Bye-bye.